A microscopic understanding of how a gas behaves enables us to understand a macroscopic quantity, in this case the temperature of the gas, which can be measured in the real world with a thermometer. The molecules move at random and exert a pressure while making elastic collisions with the walls of the container. As the temperature increases, so does the average kinetic energy of the molecules. As the molecules move faster, they collide into the piston harder and more often, causing the volume to expand. As the pressure increases, the volume decreases. As the temperature decreases, the volume contracts. In reality, there would obviously be a huge number of tiny molecules moving about within the cylinder to create the trends shown, rather than just the few shown. Now let's see the patterns graphically. The pressure and the volume are inversely proportional. This pattern is known as Boyle's law. Therefore, if the temperature remains constant, pressure multiplied by volume remains constant. The temperature and the volume are directly proportional. This pattern is known as Charles's law. Therefore, if the pressure remains constant, volume divided by temperature measured remains constant. Combining Boyle's law and Charles's law gives an equation. PV divided by T is constant. This equation applies to a pressure or a temperature change for a fixed mass of gas. The constant of proportionality is nR, where N is the number of moles of gas trapped in the container, and R is the molar gas constant. The rearranged equation PV equals nRT is known as the ideal gas equation. The ideal gas equation is derived from experiments. We will now look at a gas law predicted from theory that applies the laws of mechanics and statistics to a simplified model of an ideal gas. By applying Newton's second law to a single particle in a box, it can be shown that pressure times volume equals mv squared. As 1/3 of the N molecules are moving on average in each of the X, Y, and Z directions, pressure times volume equals 1/3 nmv squared. As the molecules are now moving with random speeds as well as in random directions, the equation is now written as PV equals 1/3 mc RMS squared, where CRMS is known as the root mean square speed for statistical reasons. This final equation is known as the kinetic theory of gases equation. We can now equate the right-hand side of the two equations, replacing small n, the number of moles, by n divided by Na. Notice that n cancels. But R, the molar gas constant, divided by Na, Avogadro's number, is known as the Boltzmann constant K. This allows us to simplify the equation. This last equation implies something quite profound. Let's see. By multiplying both sides of the equation by 3/2, we can make the left-hand side resemble the kinetic energy formula half mv². The left-hand side describes the average kinetic energy of a gas molecule. This kinetic energy is therefore proportional to the absolute temperature in Kelvin. We can see that the average kinetic energy of gas molecules depends only on their temperature. This is a good example in physics of how the microscopic, the mean kinetic energy of the gas molecules, can explain a macroscopic property, in this case the temperature of the gas, measured in the real world with a thermometer.